Hi, my name is Dominica, and today I will present our paper Open Sesame, Introducing Access Control to Voice Services. You might be aware of the increasing presence of smart home assistants in our everyday lives. We can ask them to play music or set up timers, and they are really quite convenient. The issue is that they are also quite vulnerable. So one example are hidden voice commands, which are hidden perturbations within a YouTube video or a song, and it will trick your assistant into executing a specific command. And you can also be subject to record and replay attacks, and in that case an adversary has recorded you via a compromised device, such as your phone, and then replay the attack to your assistant, which will then execute that command. So how can we restrict access to only authorized users? So the first thing is to understand how voice assistants work. So voice assistants usually work with a platform with a series of third-party apps that you can call to ask for weather or play music or party games, whatever you want. But they can also control your smart home devices with many different functionalities. So if we take Alexa and Google Home, which are the two most popular voice assistants, they usually divide their functionalities into different interfaces. So Alexa has a high-level interface such as smart home security, for example, and capabilities, which are the actual functions such as lock or camera stream. And Google, in turn, directly lists all of his functionalities under the traits name and also lists devices type and recommend for each device a specific functionality. So let's have a look at an example of a voice command. I will not read it, not to activate your devices, but we can see here the trait or the functionality, which is lock, and then the device, which is in this case the garage door. So previous work already investigated access control in the domain of smart homes, and they looked at how to design and enforce policies within such an environment. The problem here is that they do not look at voice assistants and the added challenges of the voice interface. So Sesame et al. Presented a sensitivity analysis on voice assistants specifically, but they simply extract keywords from commands and to determine whether it is sensitive or not. So the many issues come from the fact that there is no enforced access control on voice services, and also commercial voice assistants leave that decision to developers whether they want to add second factor notification or not on their apps. And the work presented by Sesame et al. Is too simplistic for an environment that have many users, devices, and functionalities. There's also the additional concern on privacy and the fact that you're sending your voice recordings to cloud servers that you don't necessarily trust. Which brings us to the many challenges of implementing access control for systems with a voice interface. So usually in an operating system, you know exactly the functionality to be executed and can easily enforce your policy. But here we have to find ways to extract the intent from the spoken commands. And to do that, we have to perform this extra step of semantic analysis. The system must also be efficient on local devices and also accurate to preserve the usability of voice services, since the reason to use voice in the first place is because it's fast and easy to use. But we also have to make sure the system can detect sensitive commands. So we present to you Sesame. So Sesame is a framework that extracts the functionality from the spoken command and checks it against a policy and possibly invoke an authentication step that leads to the execution or not of the command. So we identified three key components to build Sesame. So first, we use an automatic speech recognition model to transcribe the command into text, which we then feed to our natural language processing module that will perform the semantic analysis and extract the trait or the device from the command. And finally, our access control policy that determines whether or not to allow this particular command and enforce the policy. So let's walk through what it looks like when the system receives an authorized command. So we have our authorized user that will say the command, which is then captured by his device, and that device has the policy module already loaded. So the command is then transcribed by the SAR, and the NLU module will extract the trait and the target device. And this is checked against the policy we have loaded, and in this case, the user is successfully authenticated, which in turn opens the door. Now let's look at a malicious command. So here we have an unauthorized party that was able to play a hidden command or play a recording, which will trigger the voice assistant and that will transcribe the malicious command. And then you will extract the corresponding functionalities. But when we check the policy, it detects a sensitive command, and so it will trigger an authentication step, and this will fail, and the command is not executed. So in this work, we aim to answer two questions in particular. So first of all, how accurate can our NLU model be, and how efficient it is on the edge? So to this end, we will evaluate different model architectures in terms of their accuracy on the classification task and also their efficiency on the device. So we also evaluate them on end-to-end with the added ACR module. So the classification task consists in extracting the target interfaces correctly. In this presentation, we will take Google Home as an example, but we also perform the same experiments on Alexa, and you can find more details in the paper. So we collected for Google Home 25,000 utterances from the App Store, and we manually labeled it for traits and devices based on the documentation and example utterances that they provide for each interface. So in total, we have 28 traits and 49 devices. And in our experiments, we report the accuracy over all classes. The architectures we consider are two transformer-based models. So first of all is BERT. It's a widely used model for NLU task, but it is quite big with 110 million parameters. And so we compare it to its compact form, mobile BERT, which is a fourth of its size. We also perform quantization on both models. So quantization is a technique that reduces the floating point precision to speed up the model and also reduce its weight. And in this case, we reduce our 42 bits floats to 8 bits. So let's see the results for the first experiments. So here we see the accuracy on all classes for the trait classification. So we see that BERT has a high accuracy with 98.84, and also what's interesting is that the smallest model that also has been quantized performed just the same. And when we add the extra error induced by the ACR, the accuracy is slightly affected, but still remain high for all models. Similarly, the accuracy on the devices task is very high, with again little loss from the quantization, and also from the end-to-end setup. So in practice, you would define a set of traits that you find sensitive so you can then apply the policy. And so it is interesting to see how well our models perform on security-related classes. So here we define sensitive traits and devices based on the functionalities for which Google Home documentation recommends second factor authentication. So devices such as lock, camera, contact sensors, security system, doors, gates, as well as all network-related functionalities are all marked sensitive. And we evaluate our smallest model, mobile BERT Quant, on that task. So the results here show that the precision, recall, and F1 score for the sensitive classes for both traits and devices, and their end-to-end setup. So we see the models have a high recall on the sensitive classes, which indicates that it would be effective at catching them and enforcing policies. But we can also see that precision is also quite high, which means that the utility will also be high. However, the added error of the ACR seems to affect the performance of the models, and it's possible that key sensitive words were wrongly transcribed, which in turn affected the performance. We now move on to the second question, which is the system efficient and can it run it on edge? So to this end, we implement Sesame on an Android 10 phone with 8 GB of RAM and 8 cores, and we run our experiments 50 times. And we record the inference time for both models and end-to-end, and also the memory usage and storage space. So first of all, in terms of space, we show that we were able to go from 405 megabytes with BERT to 24.5 with our smallest model, and while conserving similar performance on the classification task as we've seen earlier. And similarly, in terms of inference time, our smallest model ran an inference in 244 milliseconds compared to the biggest counterpart, BERT, that runs in 1172 milliseconds. And the ACR adds a small overhead. And finally, the memory usage is also reduced from 404 megabytes to 126 megabytes. So, in this work, we present Sesame, which is a framework that provides a fine-grained access control for voice interfaces. It is lightweight and efficient, and we successfully demonstrated on two popular voice assistants such as Alexa and Google Home. Thank you very much for your attention.